continue with the polymerization processes. If you remember, last week I introduced you one of the desktop, let's say, SLA systems, Formlabs 2. And if you remember, to the end of the quiz, some of you have watched the washing process. Now I will show you briefly the curing process. Let me stop sharing. So here you see we have SLA system. This is printer, a photopolymerization printer, and this is the washing unit. We have, if you remember, isopropyl alcohol. We set that IPA, and right now the part is okay. It's clean, but its strength is not that good. You can easily break it. It's not fully cured. Now, with the help of this heating system or just curing system, we will be curing this one for about 15 minutes, or let's say, I think it will be 30 minutes at 60 degrees. By using the simple button, you can arrange the temperature and the time for the post-curing operation. Now, in a moment, it will reach to 60 degrees, and I can start the heating process. But let me open this one and show you the interior. Right now, the interior is about 50 degrees. We have a kind of a rotating table. This will be rotating. In a moment, you will see that once its temperature reaches to 60 degrees, it will always rotate slowly, so that all the parts, all the interior of this part will be cured in a homogeneous way. If you just keep it, then you will not be having homogeneous curing operation, since we only have lights, UV lights on the right and left hand side. So if you do not rotate it, then just left and right part of it will be cured. So right now I'm closing it, and yes, this one is going to reach 60 in a moment, maybe in 5 minutes, and then for about 30 minutes it will rotate and cure the product. Any questions about this, let's say, curing unit, guys? No questions? Okay. Then I can continue with the... Sure.
Bu post curing'in tek amacı strength'i arttırmak mı?
Yep, that's the only reason we do the curing operation. And we don't want to have any actually uncured photopolymer inside the part. We want to fully polymerize all the things, all the material. Otherwise, you will not reach the, let's say, strength values which are defined in the manuals of the materials. Yes, let's first summarize what we have discussed. We didn't actually gone through the slides a lot, since I spent most of my time on the machine. Let me open the chat. Yes. There's a question why we didn't actually remove the supports before curing. We will be doing it after the part is cured. Since if you remove it right now, the part actually has not reached to the full strength, you may deform the critical region. So that's why we will wait for the full strength. Once it reaches to the full strength, then we can remove the support structures.
Hocam supportlarda o zaman full string'e ulaşmış olmuyor mu? Daha zor olmaz mı?
Yep, but they have just little connections with the part. It's not difficult to remove it. In a moment, I will show you, and you will, I think, agree with me. We discussed all these advantages, disadvantages. With this one, we can produce highly accurate parts. We may use materials with flexibilities. We can use materials having castable properties or high strength properties, toughness, high toughness properties. And on the other hand, we need to use the same material for the support and the building material, building part. We cannot use secondary material. So this might be an advantage or disadvantage depending on your application. And we can easily produce some medical products with it, and most of the dentists and also some medical doctors prefer to use such materials, such process in order to print some replicas of organs or tissues. They are mostly using SLA type of printers. What are the cons? What are the drawbacks? As you see, we need to do washing, post-curing. There are many operations. Another thing, if you do lots of, let's say, more time, if you spend more time on curing, then you may have some warpage around the parts. And the part is brittle. Another issue, we need to have support structures, and these support structures need to be removed. And sometimes, not all the time, but some of the materials might be toxic. I don't know whether you can see or not, but this just started rotating. Let me switch to the full view for you. Do you see? I don't know. We have a purple light inside, and bring it closer. I think it's not easy to see. We have the part inside, and this is rotating in a very slow manner, so that each region of the part will be cured. And you can see the time here. In 30 minutes it will be done, and then later I can remove it and try to work on the supports, and finally you'll have the desired product. So we said that this before using photopolymerization in 3D printing industry, 3D printing, let's say, machines, people were using them for the coating and printing applications. And we also use this kind of actually photopolymers in dentistry. They actually put these material into the openings around your teeth and try to fill them with these photocurable resins. For the radiation or for the curing, we may use different type of sources. May use gamma rays, X-rays, electron beams, UV light, or simply visible light can also be utilized. And we will see now that there are 3 types of photopolymerization. The fundamentals are the same, but the configurations are a bit different. What are these configurations? And this one, the first one, is called as vector scan or pointwise. And in this pointwise systems, we have a kind of a laser, so it moves point by point around your, let's say, slice and do the curing. So we can also name them as line-wise, since our laser is moving continuously. By moving the laser around your photopolymer, you can cure the whole layer. Or in the mass projection type, these things are a bit different. This is called as layer-wise. Assume that this is a kind of a layer, and assume that this part is the desired region. We want to cure this region, and we do it layer by layer. We don't have a laser or kind of point moving all the time. We simply cure it at a time. This is a very time-efficient approach. And then in the last one, in the last configuration of the photopolymerization, we have 2 lasers, kind of photons. With the help of it, we try to cure very detailed regions, and you will see that with the help of that configuration, we can produce parts around some micrometers. But we don't have a commercial product about it. Later we are going to discuss it. But right now, let's start discussing each one by one. Here you see the first one, the vector scan approach. As opposed to our configuration this time, in this main configuration, our VAT is moving downwards. And in this vat, we have material all around, material inside, we have resin, and the platform, as you see, is moving downwards. And once it's moving, always our part, the solidified regions will always be inside this vat, and we will always have around liquid resin. It's not shown here, but obviously we need to have some support structure underneath, especially these regions which do not have any material, any solidified material underneath. But the fundamentals are the same. We need to have slices, since it's an additive manufacturing technology. Let's focus on this upper part. This is the laser, and we have some optics for focusing. And then this is the most important part, the galvanometers. And these are kind of mirrors, and we discussed them. They are lightweighted, and with the help of it, by simply rotating them in two orientations, you can reflect your laser any points on this plane, on this XY plane. And he said that since the weight of these mirrors, the galvanometer is very light, we do just around some grams maybe. So that's why this is much faster than rotating the laser or moving the laser. We prefer to keep the laser in position and move this light, actually orient this light, this laser beam with the help of the galvanometers. We have another orientation, another configuration, very similar to the first one, but the difference is that this time we are moving the platform upside, not downwards, and the rest is the same. Again, we have the laser, some optic equipment here, we have the mirror, galvanometer, and it's reflecting the laser beam on the plane. As you see, this is laser beam. We have again the tank, and this time our platform is moving upwards. These regions are cured already, but the part here is not cured. This region is, some of the regions are here, actually inside the tank, they are cured, but this is the layer right now being processed. And by moving the laser all around the XY plane, you can cure it. Once that layer is cured, you can move your actually platform some amount which is equal to the layer thickness, and then continue with the curing operation of the next layer. And these days, some of the actually printers do not have any X or Y motion. So how do they do the removing? They simply remove this part. Remove this, let's say, this Marvin, by the way. They remove it with an initial, let's say, force. Since once secured, it will stick to the plane, stick to the glass. So you need to apply a little bit more force to remove it from this glass. And then later, some of the printers have a kind of a sweeper. They sweep the glass so that it will be cleaned and will be ready for the next curing operation. But some do not have such a weeper or wiper, and they can simply move it upwards and then downwards. So some of you were curious about how we remove the supports. As you see, it's a very small gear, and now I'm going to remove that supports underneath. You see there are supports underneath. By simply applying a torque, see, they are all removed. Now we just have the gear, but obviously there are some marks underneath. Yes. It's not easy to see, but there are some marks due to the support structures we utilize, and I need to use it since this is a simple product, but it's better not to print the part directly on the plate. If you do it, then it will be quite difficult to remove it from the plate since it gets sticky, and while removing it, you need to apply forces, and this will do harm on the teeth of the gear. So that's why I prefer to actually print it with the help of supports. Since the bottom face is not important for me, having such scratches, having such marks are not a problem for me. This is the second approach. We will discuss the details, but just an introduction. In the second type of configuration of photopolymerization processes, we use kind of an UV lamp, or this a kind of projector, a special projector. We reflect the images on the plane, and this slice is cured at a time. So once you reflect the image, you don't need to do anything else. You don't have a laser which needs to be doing some scanning. This is not the case in mass projection type of approach. We simply reflect the image on the plane and do the curing operation. And this DMDs are digital micromirror devices from Texas Instruments. These are patented. And if you use a kind of a projector which is using digital micromirror devices, then these all parts will be inside a single projector. So by simply using a single projector, you can reflect the images, and the white portions of that image will be cured, and the black portions will not be cured. This is the last configuration, two-photon approach. We'll discuss the details, but we can keep in mind that in this one, we are using two lasers, and we do the curing operation inside the vat. And we don't have actually a platform which is moving downwards or upwards. We simply do the operation inside a tank. And in our textbook, we don't have this, the last approach, continuous digital light processing, but it's a very popular one these days. We have another name for it, but we can right now say that this is continuous digital light processing. Very similar to the first one, the middle one, digital light processing or mass processing. The only difference is that in the last one, our plate is moving continuously. We don't have slices, but it's moving continuously. The difference is that we have a secondary kind of chemical reaction, and with the help of it, we can have smoother products having better properties. So now let's go into some details regarding the materials. So you know that we are using photopolymers in this type of printing processes, and we prefer to use UV curable photopolymers. There are also some gamma rays, X-ray curable photopolymers, but they are obviously expensive and difficult to use on like desktop type of 3D printers or SLA systems. We prefer to use photopolymers, and they are all UV curable. And people were using these type of photopolymers mostly in microelectromechanical systems or microelectronics industry, and they were using them as photoresist materials. And the thing is that they didn't have multiple layers. They were just using a single layer and then do the chemical reaction and try to remove material from let's say, coated regions. But obviously in SLA technology, we use it for many layers and try to produce complicated 3D shapes. And for the lasers, we don't need to use carbon dioxide type of complicated lasers. We can simply use helium, cadmium, or neodymium type of lasers, and their powers are not too much. Very low powers can be utilized. Any questions, guys, up to this point? I will be discussing the details of now materials, the photopolymers, why they are different from the conventional polymers. You'll see on this upper part, we have some examples of thermoplastics polymers. And in such polymers, we always have longer, let's say, branches. This is a linear version. We don't have any branch, but we may also have branched linear polymers. You see, they are continuous, and sometimes they may have such extra branches around. but in summary, they're always linear. And the thing is that we can do manufacturing operation with these polymers, and then after the part is ready, and if you're not happy with the part, you can simply recycle them. But if you look at the photopolymers here, we have longer branches, longer linear branches, and they are also connected to each other. We have links between these branches. And this is actually the fundamental difference between the thermostats and the thermoplastics. And that's the reason actually we cannot reuse, we cannot recycle the photopolymer products, since with the help of the photopolymerization, we have these links formed between the branches, and you cannot remove it by simply heating them or doing some operations. So this is not a recyclable material. So what do we have inside these photopolymers? In the earlier days, while people trying to invent such photopolymers, they simply use acrylate type of compositions. And the problem with that compositions was a huge amount of shrinkage. You see, sometimes if you just purely use acrylate compositions, we may have up to 20% of shrinkage, which means that if you have 10 centimeters of part, then after curing and after all operations, its size might be decreasing to 8 centimeters. And then they start to use just epoxy compositions. And the problem of the epoxy composition is that you need to spend more time on curing. You cannot actually cure it by using a very high-speed technology. You should be curing it slowly, and that takes lots of time. Another issue is that the cured products have high brittleness, and this is actually again not preferred in stereolithography. We don't want to have brittle products. Another issue, the last issue, is that the epoxy compositions are very sensitive to high humidity levels, and their properties do change a lot once you have humidity around. And later, they simply actually joined these acrylate compositions with epoxy compositions, and they were quite successful. The strength of the products are improved, and also the problem of the epoxy composition is eliminated. Right now, the brittleness is decreased to very low levels, and now with the help of this new composition, having acrylates inside epoxy compositions results in a good, let's say, composition, and we can use them in our stereolithography or in our printing processes. And what do we have in this photopolymer materials? We have 5 different products. We have photoinitiators, reactive diluents, flexibilizers, stabilizers, and lastly liquid monomers. But the most important ones are the photoinitiators. As the name implies, once you start the radiation, these will be initiated. With the UV light, they will be initiated, and we will have some reactions between the monomers and the initiators. So with the help of this UV light, these are the monomers. And once you start the process with the UV lights, and then we will have such branches, such connections, such links between these monomers. So these are the most important items in the photopolymers, in the photopolymer materials, the photoinitiators and liquid monomers. So how we do the photopolymerization? We need to have the radiation, and we do it with the UV light, and then our photoinitiators become reactive with the monomers, and then chains are started, built across the monomers, and with the help of it, we will have cross connections between the monomers, and with the help of these steps, we will have a solid material. That's why it's called an polymerization, and it's literally the process of linking small molecules into larger molecules. So in this polymerization processes, we have small monomers, and once the process is started with the help of the UV radiation, we will have such crosslinks between these parts, and with the help of it we will have a larger molecule. So this is the larger molecule, and the smaller ones are simply the monomers themselves. So this is the chemistry, the simple chemistry behind the photopolymerization. Let's now have a look at some modeling or some relationship between the amounts of monomers, photoinitiators. Obviously, this is a highly complicated process and people didn't come up with a complete analytical model. They have some relations between the amount of monomers, photoinitiators, but they cannot write the whole process in an analytical model, since, as I said, it's a very complicated process. But we may discuss some relations between the reaction rates and the molecular weight of the polymers. Let's focus first on the reaction rate. And this is the reaction rate of our photopolymerization process. And we have two important variables. The first one is the amount of monomers and the amount of photoinitiators. So if you look at the reaction rate here, it simply depends on the consumption rate of monomers. So we can say that if you put too much monomers on your, let's say, composition, then that means your reaction rate will be higher. And as you see here, it's directly related with the amount of material you are consuming in unit time. And it's also related with some other parameters, but the most important parameter here is the amount of monomers consumed in unit time. It also depends on the amount of monomers and also the amount of photoinitiators. But the thing is that it depends on the square root of photoinitiators we have, and also there is a parameter, a constant K. So it does depend on the amount of photoinitiators, but not as much as the consumption rate of monomers. Since if you double, let's say, the monomers, the reaction rate will also be doubled, but if you double the amount of photoinitiators, it will only be affecting it by the square root of it. So it will be increased by just 1.4. But once you double the amount of monomers, the reaction rates will be doubled, and it's not the same for the photoinitiators. Once you double it, the reaction rate will only be increased by 1.4. Any questions, guys, about the reaction rate?
Hocam, not about the reaction rates, but I have a question. When reçine kullanınca sararma yapıyor mu bir süre sonra?
What do you mean by sararma?
Yani reçine olunca bazen şeffaf reçineler başka epoksi falan kullanınca ileride sararma yapıyor.
I think it's just about the post-curing process. Even though you finalize your curing operation, and then you put your part, let's say, in your room somewhere, with the help of these lights, the reaction will continue. So the curing will not complete at 100%, maybe up to 95%. So in time, you may have more curing operation. That might be the reason behind colorization, but I'm not sure about it. I should check it, since I'm not doing any research. I'm not an expert on photopolymers, but that might be one of the reasons. Any questions, guys? Any other questions? So let's have a look at the second issue here, the average molecular weight of the polymers. As you see, it simply depends on the rate of the reaction and also the rate of photoinitiators. So we have a relation between these. And if you increase the reaction rate, then you have let's say a larger molecular weight or a higher molecular weight for the polymers. But if you decrease it, then you will have lightweight polymers. Another thing, if you have high amounts of, let's say, photoinitiators, or if you consume them in a short amount of time, then that means you'll have a lightweight polymer. So there is a kind of a trade-off. If you want to increase the reaction rates, you need to put some, obviously, monomers, and you need to put some amount of photoinitiators. But if you put too much photoinitiators, then you will be decreasing the weight of your polymer, which may result in, let's say, less durable products. Their strength will be less. So there's a kind of a trade-off between the reaction rate and the molecular weight of polymers. So depending on your application, depending on the type of material you want to have at the end of this reaction, you should decide on their compositions. Any questions? Okay, now let's have a look at more details on the vector scan stereolithography. You already know these issues, so I think I may directly try to show you this video.
Hi.
Oops, you have an ad here. So after ad is removed, I will show you the video. Any questions, guys? While I'm trying to prepare this one.
Hocam, is there any relationship between the type of radiation and the strength of the product?
Yes, obviously it will affect the type of laser you are using, the type of light, or the, let's say, rays. It will affect the quality of your part. So now we will see.
Sorsam ama.
Question?
Evet hocam, bu birbiriyle linkli olması fotopolimerlerin termosetlere göre o da string'i etkiliyor değil mi?
Yes, but not too much. Since it's a polymerization, for sure they will be linked together. But for strength, we have, I think, other issues. But as I mentioned, I'm not an expert in photopolymers. Yeah, it might be an effect, but not the only thing. So this is the same printer I have. And as you see, they have printed more complicated products. We have laser, as you see, scanning the layer.
By a couple of engineers and designers from MIT who raised $2.8 million to build the first Form 1.
So at each layer, after each layer, they have a kind of wiper. It wipes this glass so that it will be cleaned and is ready for the next layer.
But today, thanks in large part to the feedback from the Kickstarter community, and
We can see how this laser is scanning the layer.
40 years of research and development, Form Labs is back with the Form 2. Now, this one is very different from most of the 3D printers you see on the market today. Now, those models operate kind of like 2D printers, but instead excrete molten hot thermoplastics from an actual print head. The Form 2, however, continues Form Labs' stereolithographic model. Stereolithography was actually the first 3D printing technique to be invented, and it uses a blue-ray laser that actually traces part of the model image onto the surface of a bed of liquid resin. The orange cover blocks ultraviolet lights coming in that then hardens the sliver, and the process starts again as the completed object is slowly lifted out of the resin bath, layer by layer. As complicated as that sounds, I checked out an early look at the model at a briefing last month with the Form Labs team, and it's actually a very simple process for the consumer. You just unpack the printer, install the removable print tray, and insert one of the new resin carts.
You see there are different types of material. They have flexible material, castable. Castable means it's used for investment casting process. For instance, you produce the ring, a complicated ring maybe, and then put it into a kind of a mold and then pour slurry around. And then once you put it inside an oven, that material will be evaporated. So if it's uncastable, then we understand that this material can easily be evaporated in an oven. And then they have tough material. Clear is just the material they were working on. It has no color, white, black, and gray.
Directly into the machine like you would any ink cartridge on a 2D printer. The new model even adds a touchscreen display for managing print jobs and a Wi-Fi connection that'll automatically send progress updates to mobile devices in case you want to step away from.
This is what we have done, and as you see, in the earlier days, their support structures were primitive, but now they have much better interface.
For a while, or if you're planning to share it amongst several users. So why stereolithography? Well, one thing is that these printers can add a level of detail that standard fused filament printers can't. And that's whether you're printing something big.
So these are the rings actually I mentioned. These are for investment casting. So probably they have fabricated this one for using castable material.
Or something super tiny like a ring. The ultra high resolution also does a good job at hiding the individual layers of plastic from plain sight. You can barely even see the lattice pattern formed by the plastic layers, which really makes it seem like the objects were cut from one solid piece of plastic. You can buy the Form 2 right now for $3,500, which includes the 3D editing software, resin, and a finish kit for post-processing. You can read more details about the upgraded Form 2 in the full first take, but that's going to do it.
Okay, now our curing operation has just finished. So I will now take it out. This is now much stronger. Now I can maybe remove some of them by hand, but it will be quite difficult to remove the structures inside the part. For instance, this one I can easily remove, but it might be better if I use some mechanical tools, since I may harm the workpiece. Yes, I removed most of them. You can see there are just few of them remaining inside. By spending maybe 5 minutes, you can have the desired product. Any questions, guys?
Kaç derece çıkarmıştık?
60 degrees, and I cure it for 30 minutes. Depending on the material, they have different temperatures and different curing times. It's not the same for all the materials. There's a question whether we have castable materials for FFF. I think yes, we have some filaments, and you can do casting once you have used such castable filaments in your FFF printers. So now this is showing you the main structure of stereolithography systems machines. So what do they have? They have 5 main units: the recoating system, platform. This is moving upwards, and recoating is moving in X direction. Then we have vat system that is flowing, material is flowing into the vat. We have a kind of a vat, and material is always flowing from somewhere. And we have laser optics. We need to reflect our laser with the help of the mirror. And then we have control system, which is responsible for the control of all these operations. Some of them are controlled in an open loop manner, some are in closed loop manner, since you need to check the temperature, for instance. If the temperature is low, then you can turn on your heaters, resistors, so that the temperature of the environment will be at the desired level. Another thing you need to control is the beam, the lasers, the mirror, the orientation of the mirrors should be controlled. And sometimes you may have sensors about these mirrors and check whether they are at the desired position or not. And lastly, you need to control the whole process, do the scanning, move your platform upwards a little bit, clean it, and then move your platform once again downwards. So all is done with the help of the control system. And in the laser and optic system, we have beam generation, obviously, in this box. The laser is generated, and then this laser is actually reflected through the lens on the plane, on the XY plane. And for the wet system, some printers have resin level adjustment systems. They check the amount of material in the wet. If it's low, then they open their, let's say, gate at the bottom of the tank so that more material will be poured into the tank, and they will continue with the curing operation. And for the platform system, we have the elevators moving in Z direction, and for other motions, we have drive systems. And for the recoating, we have blades, and also some systems make use of it for delivering the resin. But in my printer, in SLA, in Formlabs 2, they don't use the blade for the delivery of the resin. So let's look at some of the properties of the stereolithography methods. Obviously, we know that they are highly accurate. Their surface qualities are much better. For instance, if you look at it's quite difficult to see. Let me close. But I can say that their accuracy is around 2000, and especially for the up-facing surface or the bottom-facing surfaces have sub-micron surface roughness. So if I measure the surface roughness of this bottom layer, probably it's less than a micrometer. But for the inclined surface or for the side surfaces, they are around some, let's say, 30 or 40 micrometers. Now we can start discussing the details of the, let's say, curing process, how we do the curing. Let's have an introduction today, and then we will go into details on Thursday. And we will actually try to determine the amount of curing, the depth of curing. This is the depth of curing, and assume that our laser is moving in this direction. While it's moving, you'll always have such semi-elliptical shapes, and this is the cured photopolymer, cured resin, and we will try to determine this amount, the curing depth, which will directly affect the layer thickness in our process. And for the modeling part, we need to have some variables, and these are the variables. The first one is the curing depth, and then we have depth of penetration. This is actually a kind of variable obtained by calculating the 37% of the irradiance at the surface. So you need to know the irradiance at the surface. Once you know it, if you can simply multiply it with 0.37 to obtain the depth of penetration. And then we will have some parameters about the energy, which is exposure. So this is the energy we apply on the material, and we call it as exposure. And we also have critical exposure, so which means that if you apply this amount of energy on the material, then it will be solidified. So that's why we call it as critical exposure. So the amount of energy you are applying on the material should be higher than EC, so that we will have curing operation. Otherwise, you will not be able to start the curing process. And we also have another parameter related to energy, the maximum energy or maximum exposure. This is called as peak exposure, Emax. And then we have some power related parameters. This is H, and H of X, Y, and Z is the irradiance at that point. At that X, Y, and Z point, we are trying to determine the irradiance, which is the power, radiant power at the given point or the given area. And the other one is about power of our laser. So it is a given variable. We know this variable at the start of our modeling part, modeling, let's say, process. And then we have the speed of our laser. Again, we can assume that this is known since we can easily control the speed of our laser. Another issue about the laser is the radius of the laser beam. If this is our laser beam, obviously this will be the radius and this is W0. And that will be affecting actually our modeling again a lot, but we can still say that this is a known parameter since at the beginning of the process, we can set this radius by using a different laser beam or using different optics. So that's why these are known parameters. And we have some parameters related with material, for instance, this critical exposure. This highly depends on the material. For instance, if you have a difficult to cure material, then that means its critical exposure value should be higher than ordinary materials. And another thing, depending on the material, is the depth of penetration and the curing depth. We will talk about these on Thursday. We don't have much time now, so I don't want to start the modeling. We will be discussing it on Thursday.